Hello everybody, and welcome to these lectures on computer architecture. I'm again still going to continue a little bit a halfway point, the summary of the digital systems. Well, for those of you who already know, you can just skip it, but maybe you just want to hear some kind of summary of where we are standing. So first I want to show you something remarkable, and that is about the feature size. About how big the transistors, how big the processors are. So I've taken here a picture of what is called a Prescott 2, which is the Intel family, Intel Pentium family, one of the latest, I think not the latest, but one of the latest. And it has so many transistors, millions and millions of transistors, that in fact they're getting smaller and smaller and smaller. And to give you an example, here we have the one of the first, or by many considered to be the first processor, computer processor, the Intel 4004, and that one had about 2250 transistors. And each of these transistors, they of course occupy the space. It's a two-dimensional object, and the size of the transistors, or actually what we call the feature size, which is part of the transistor, for instance the gate or the source or the drain. So the feature size of this Intel 4004, and we're talking about the 1970s, had 10 micrometer feature size. And the modern technology of this Prescott 2, which, Prescott 2 is of Intel and Ryzen is of AMD, and AMD is even a little bit ahead at the time of Intel. Of the Ryzen and the Prescott then more or less is 10 nanometers. 10 nanometers, I should say. So that is a factor 1000 smaller, meaning that on a square area you can put 1 million times more transistors, because 10,000 micrometer squared is 1 million times 10 nanometers squared. So now you can imagine that on each the size, the area of an original Intel 4004 transistor, there can now fit 1 million new transistors. And considering the fact that the Intel 4004 had 2250 transistors, you can stack about 4000 full 4004 processors on the area of what before contained just a single transistor. Just to give you the scale of things, the innovation that has been going on in technology. Well, that is just the introduction of these lectures, the second part of computer architecture. So with that we can go on. Actually, I want to mention to you that this entire subject of information processing, computer architecture, or in general informatics in general, it has three aspects. The first aspect, we have the numbers. As you know, the numbers for mathematics. So these are like binary numbers and things like this, and we're going to talk about in the next summary. But the other thing is that we have the numbers. The other thing is we have the electronics that then implements the numbers. Or actually to say there's something in between. There is the logic. So we have three basic aspects of this subject, which is the logic, that is the Boolean logic, that things are true and false and so on. Then we have the numbers that can be represented by the logic of Boolean algebra. And then we have the electronics that then implements it in the real world. So these three things, I will now give you a small summary in the next 10-20 minutes, meaning I will probably cut it here in half. Doesn't matter where I can start. I can start with the electronics, or I can start with the numbers, or I can start with the logic. It doesn't matter. In this case, I will just start like I did last year also. I will start with the gates. Or the logic operations, no matter, depends on how you're seeing this. So any logic operation or logic gate, because they are binary, because we're going to talk about logic, which is true and false, that kind of logic, meaning that any value, any line, any signal, or any piece of information can have two values. And if you take then processing this information by a gate or by a Boolean function or something like this, then you can have that the simplest is that you have two of those inputs and one output. And if you have now two inputs that each can be binary, and with one output that is a function of these two inputs, then I can imagine that there are 16 different of such logic operations. Two inputs, each have two possibilities, so you have 2 to the power 2 to the power 2 input combinations, and each of them describes one output combination, so you have then in this case you can have 16 possible logic gates. And I've plotted them here, all of them, and most of them they are completely silly. For instance, let me give here, they're all 16 are here. One of them, for instance, this one, the output of this one here on the right, I don't know if you can see this here in the bottom right, this one, the output is always 1, or is always 5 volts, or is always true. Well, I would not call that a logic operation, I would just call it a power supply, if it's always 5 volts. In the same way, you have here on the top left, it's always 0. Well, I would call it just ground, it's always false. That is not what I call a logic operation. And other things, for instance, also, although they have two inputs, the output is always A. It's just copying A, like you can see in this one here. That's also not what I call a logic gate. So what we remain with is basically we have 6 binary, that is to say 5 useful binary operations and 1 useful unary operation. And those are these 6. And I have here even a better picture for you here. I will put this one, which I like. We have these 6 logic operations that are more or less the basic operations. So we have the NOT, that is a unary. It just inverts the input signal. We have the AND, the OR, the NAND, the NOR, and the exclusive OR. So 5 binary operations, meaning it takes 2 inputs, and 1 unary operation taking 1 input. All the values, of course, are binary because we do binary logic as we have agreed on in computer science. So now the thing is, of course, where do we go from this? Are we going now to start explaining how to do all the logic functions? Or no, wait, I'm going to stop here a moment and I'm going to tell you then, well, how is it implemented in electronics? And I've done here somewhat older technology that nobody uses anymore. So I will not even talk about this. It's better to talk about CMOS technology. So these are the truth tables. So I should forgot to say this. These are the truth tables. That's okay. I'm sure that you know all this. The NOT, OR, AND, exclusive OR, NOT OR, and NOT AND. That's all very nice, but how to implement it? So we can do this with MOSFET transistors. And a MOSFET transistor, metal oxide semiconductor field effect transistor, that is basically, it's just an interrupter, as if you have a light switch. You have an in signal that basically switches on conduction between the source and the drain, or I just called them here A and B, or B and A, I should say then, in A and B. And you have 2 types, P channel and N channel, all very nice. If one conducts, the other doesn't conduct. And with this input signal, we can basically make this channel here conduct or not conduct. And then we say it conducts completely or it doesn't conduct at all. We say it is on or it is off. And on basis of this, it's digital electronics. We can make, for instance, our first NOT gate. Don't forget, these are where were they? These 6 are the ones that we're trying to make, these 6 gates. And then we will see that with this we can actually do anything else that we want, any logic function. So the first one is the NOT. What did we do? We just placed 2 complementary transistors. One is P channel, the other one is N channel, so they're never both on conducting, and we just connect them to the input A, and then the output is actually not A, because if A is high, then this one conducts and the output is connected to ground and the output is 0. And if this one is low, this one does not conduct and this one conducts and the output is connected to high, which is a logic 1. The funny thing of this is that there is never a conduction path between one of the power supplies and the other, and that's why we save power. We never have a leakage current, and that's why we call it complementary metal oxide semiconductor technology, or CMOS technology. So a NOT gate we make from two of those transistors, complementary transistors, and we have a NOT gate. Then we have the NOR gate. How do we make a NOR gate? Well, just go back to the lectures. It's there in the previous set of lectures about digital electronics. And what we're doing, we take 4 of those transistors, 2 in series, and here down here 2 in parallel, and then we will see that it exactly follows this output, this truth table in electronics, or this truth table in Boolean algebra, in ones and zeros. That is a NOR gate for transistors. In the same way, we can make a NAND gate. A NAND gate is also made up of 4. Here, 2 up there are in parallel, and 2 down here are in series. And the way we connect them, we get this truth table, which completely represents the NAND truth table. Very nice. So we have the NAND, we have the NOR, we have the NOT, and then the AND is simply the NAND plus an inverter. So that means it's 6 transistors. And the NOR is just, an OR port is just a NOR port plus an inverter. So that also is 4 plus 2 is 6 transistors. Finally, the last one that we need, this one is a little bit more complicated. An exclusive OR is then made of 3 NAND gates and 2 inverters, and then connected in this way. So as you now know, 3 times 4, that's 12, plus 2, so that is 16 transistors, and we copy the exclusive OR logic function or truth table. In summary of the electronics part, we have these 6 basic operations and the number of transistors in CMOS technology, it has to be said, is that the NOT has 2 transistors, the NAND has 4 transistors, the NOR has 4 transistors, the AND has 6 transistors, OR has 6 transistors, and the exclusive OR has 16 transistors. This you have to keep in mind when you want to reduce the number of transistors. It's better to use NAND and NOR ports than AND and OR ports, because they have simply a little bit less transistors. And finally, it's funny to note that if you want to also get rid of the NOT gate, which sometimes is not very nice, you want to keep it simple with the most elementary components possible, then the NOT gate you can actually make from the NAND gate or from the NOR gate by linking the 2 inputs together. As you see, this NAND gate is actually a NOT gate, and this NOR gate is actually configured also as a NOT gate. In this case, then we have we can get rid of the NOT gate, but maybe you don't always want to do like this. So the thing then is, because the NOR and the AND and the OR you don't need, because they can be made of NAND and NOR and a NOT, and the NOT can be get rid of if you don't want it by this technology. So in principle, you can make everything by NAND and NOR gates, which is a nice, interesting thing to do. So the next lecture of this summary, I'm going to talk to you, let me see what I'm going to talk to you about. I'm going to talk to you about the numbers and the Boolean algebra, and by then we should be more or less ready to get started with the second part. See you in the next lecture.